So we'll be going over like the basic math and coding of machine learning. We're probably not going to go over any actual machine learning today. We'll just go over kind of the technical fundamentals that make up a lot of machine learning. So yeah, let's get started. Here we go. Okay, so the data structure. So like one of the most fundamental parts of machine learning is manipulating, processing, and analyzing data. And the types of data can vary between different data sets, different data types, but fundamentally, a lot of it is largely basically working with matrices or arrays and doing like a bunch of different array multiplications with each other. A matrix is like it's an array of array of numbers that can have dimensions. So it has vertical and horizontal dimensions if it's a 2D array or a matrix. So if we look to all these things on the right, do you see how it kind of is? It's like a parentheses of parentheses, and it's like a grid of numbers. So if we look at the one at the top left, that's a 1 by 3 row matrix. It has like the values A, B, and C. The next one is a 3 by 1 matrix. It's A, B, C, but this time vertical. And then you see a matrix of all zeros that is 3 by 2 is 0, 0, 0, 0, 0, 0, right? And then you have a 3 by 3 matrix, a 3 by 3 matrix, a 3 by 3 matrix. If you think about basically just taking a grid and filling it with numbers, then you have the number of rows and the number of columns, and that's represented as what we would call a matrix. So you essentially have the rows that you have elements. So it's like a collection of elements represented in like a grid-like format. So
Okay.
so each row has numbers, each column has numbers, and then those are like the features of this matrix. Okay, so the important part with a matrix is it has dimensions, and it's represented by the rows, by the columns, and they can have like, there's tons of different combinations, infinitely many combinations of how you want to have it. So for instance, if you look at the bottom right, you could have a square matrix where it's the same number of rows and the same number of columns. And then you see the top one, 2 by 3. That means you have 2 rows, 3 columns, right? If we look, there's 2 rows. The first row, 1, -8, 5. The second row, -5, 7, 1. The first column, 1, -5. The second column, -8, 7. It's organizing numbers in rows and columns within these. They're called like it's just called a matrix, and you usually represent it with a bracket, and then the numbers inside. Okay, so matrix addition and subtraction. So just like you can add like numbers like 1 plus 2, you can add matrices of the same dimension, right? So if we look to the right, we have examples, right? So that's why we can add those two matrices together. So we call it, so when you add make two matrices together, we call that element-wise addition. So if you look to the right, what you do when you add those two matrices together is you do 4 plus 1, 8 plus 0, 3 plus 5, and 7 plus 2. Same thing applies for subtraction, right? If we were to subtract those two matrices, it would be 4 minus 1, 8 minus 0, 3 minus 5, and 7 minus 2, right? So that's what, like 3, 8, -2, 5. So then you get a 2 by 2 matrix as the output because it's the same dimensions and it's element-wise operations, right? Each element is added or subtracted with its corresponding elements. But the key thing is this only works if matrices are the same dimension, right? Think about it. If you take a 2 by 2 matrix and you add it with like a 5 by 5 matrix, it's like, what do you do with that? Like they're not the same elements. They're not the same size, so you can't just do element-wise, right? So this only works if they're the same dimension. Look at the same example below, right? That's a 2 by 2. Other one's a 2 by 2. Add them together element-wise, and then you get 5, 5, 2, 3. Okay, so more examples, right? So think about it. So a lot of times you represent matrix with a capital letter. So right, this matrix is represented as capital A. So you capital A plus capital B, right? And then capital A, 2 by 2 matrix, A1, A2, A3, A4. This is very common matrix linear algebra notation. So don't worry too much about the notation. Just understand what's going on. So you do A1, A2, A3, A4, right? Plus B1, B2, B3, B4. 2 by 2 plus a 2 by 2. And then as we've shown earlier, what you get is A1 plus B1, A2 plus B2, A3 plus B3, A4 plus B4, right? Okay, and then of course, since we've shown earlier 3 by 2, then the next one is also a 3 by 2 matrix, right? So then when you add them up, you do element-wise. So 5 minus 11, 2 plus 0, 4 plus 7, 9 plus 1, 10 minus 6, -3 minus 8, right? And then you get the solution. So the weird property with matrices is they have, you know how with normal numbers, right? If you multiply them like 5 times 5, that's just 25, right? But with the matrices, you have to be very specific with what type of multiplication we're doing, okay? So we're going to start with the simplest type of multiplication, which is element-wise. Yeah, so matrices have multiple types of multiplication. So we're going to go over the most simple multiplication first, which is element-wise multiplication. So in this multiplication, it's denoted, as you can see, it's denoted with like a little empty circle. So what you're doing is you take two matrices, right? They have to be the same dimension. Once again, if we look here, these are 2 by 2 matrices, and then we take their element product. So it's 1 times 3, 7 times 3, 2 times 5, and 4 times 2, right? So if it's A1, A2, A3, A4, again, like kind of what we showed last time, if you do the element-wise multiplication, you get A1, B1, A2, B2, A3, B4, A3, B3, A4, B4. And that's kind of, it's the same as addition. Okay, so if we look below, right, so you have matrix A, matrix B, matrix C. If you want to take the element product and they have the same dimensions. If you guys don't understand this notation, but you said earlier, don't worry. This gets into a little more like algebra notation and like variables and stuff like that. So if we have m rows and n columns, dotted by m rows and n columns, not dotted, sorry, that's the wrong word. Element-wise multiplied, you still get an m by n matrix, right? That makes sense because that's exactly what we were doing earlier. This time we just assigned like variable names for the rows and columns instead. So you need the same rows and columns multiplied by the same rows and columns to get an element-wise product. So this is the like easy matrix element-wise multiplication. So what I'm going to explain next is kind of more complicated. So we're going to go over something called a dot product. This is like also called matrix multiplication when you do this multiple times across a matrix. So the dot product is like a sort of matrix multiplication, which you do element-wise multiplication of a row of one matrix with a column of another matrix, and then you sum them up. So right, so you have the vector ax, ay, az dotted with bx, by, bz. And what you see is that, right, what does this give? You multiply ax by bx, then you add that to ay times by, then you add that to az times bz, right? And then that gives you a dot b. It's a single value, right? The other thing that's kind of weird here is that with matrix multiplication, instead of being the same size, what matters is that the first matrix has the same number of columns as the second matrix has the same number of rows. If you look below, right? If these are the dimensions of the matrices, m by n, another one is n by k. If you look above the ax and the matrix A and the matrix B example, so the reason we can dot these together, right, is because ax, ay, az, or A has the same number of columns as bx, by, bz has the same number of rows, okay? So essentially think of it as you're taking, right, a row of the first matrix, and if this is a column of the second matrix, you're multiplying them together, then adding them up, and you get the output, right? If you're dotting two products where it's m by n and n by k, the output is going to be m by k, okay? So what that means is that the two inner dimensions, if you were to write out the dot product of these matrices, those two numbers have to be the same. So when a lot of people say matrix multiplication, what they really mean is doing this dot product operation repeated for all the rows and columns of two matrices. So each row of the first matrix is then multiplied, is dotted by each column in the second matrix, right? So if it's an A by N matrix dotted with an N by B matrix, the output is an A by B matrix. This is a lot of like variable notation, but if you look at the visual representations on the right of a dot product, look, right? So AB is 1 by 2, so 2 columns, and XY is 2 by 1, 2 rows, right? Same number of columns in the first matrix as the number of rows in the second, so you can dot those together. And what's the dot product? A times X plus B times Y, so AX plus BY. So the same number of columns in A, B, C, D as there are rows in XY. But this time when you dot them, it's not a single value. If it's 2 by 2 dotted with 2 by 1, the middle two dimensions have to be the same, and then the outer two dimensions are the dimensions of the output, right? But the other way you can think about this is for each row in the first matrix, you're dotting it with the column in the second matrix, right? So you take AB, that's the first row, and you dot it with XY. That's what the thing above is, AX plus BY. But then you take the second row, which is CD, and you dot that with XY2. So then you get CX plus DY. If there were more rows, you would keep doing that. If there's another row, say EF, like below that, so it was a 3 by 2, the next output would be EX plus FY. So you just keep repeating that for all the rows, dotting them with the columns. Same thing if there are more columns, you would then keep doing that too. Okay, so now if we look at the next example, what this shows is that this is what happens when I'm saying you repeat it for every row and every column. the first element of the output is the first row of the left matrix dotted with the first column of the second matrix. And then you would repeat that for then this, so there's two ways you can approach this, either go by rows or go by columns, right? So if you want to go by columns, then you would then multiply AB by the second column, and that's the second element. So this, right, gets multiplied by this. So this gets multiplied by that. That gets multiplied by that. And then you add that together, right? So AX plus BY, right? What you're doing here is, so this is row 1, right? This is row 2. Column 1, column 2. Okay, so what you first do is you dot these two together. So that's how you get AW plus BY, right? A times W plus B times Y. And then, so that's first element, right? So first row, first column, first element, right? First row, second column, same thing you see in the output. First row, second column. You do A times X plus B times Z. AX plus BZ. So that's the first row, second column of the output, right? You then repeat that for the next row for the input. So you do CW, CD. So dy. So you get CW plus dy. Let's do something simple. 1, 2, 3, 4. Okay. Dotted with let's just go 1, 0, 0, 1. What is that? If you dot them together. Okay, so what you do here is then, so yeah, you have an output that's 2 by 2. How do we get, okay, so the reason it's 2 by 2 is this is a 2 by 2. 2 by 2, this is a 2 by 2. And then because these two are the same, 2 and 2, you can multiply them, and then it's just these outer values, so it's 2 by 2. Okay. So how do you get, so therefore this is a 2 by 2, 2 rows, 2 columns. How do we get the first element, right? So we do 1 times 1 plus 2 times 0. 1. Then we do the next column. So if we do the next column multiplied by the first row, that gives you the first row, second column of the output, right? Okay, so that's 1 times 0 plus 2 times 1, 2. Then we do 3 times 1, 4 times 0, 3. And then 3 times 0, 4 times 1, 4. And then we get this 1, 2, 3, 4. All right, examples, right? Okay, so here we look, here, right? So, all right, so you take each row, multiply it by this column, and that's this, right? Let me change colors. So then if I do this row by this column, that gives this spot. If I do this row dotted by this column, that gives me that spot. And then finally, if I do this row by this column, you get that spot. I'm going to quickly draw this out again, what this would look like. So, so you're doing this by this, gives you this, right? And then this by this gives you this. Then this by this gives you this. Finally, this by this gives you that. Okay, so why does this matter? So why do matrices matter? So most data is actually represented as matrices, right? So think about it, right? So if you got rid of all these lines and you had these values, it's basically just a matrix, right? It's just a matrix. It's just rows and columns of numbers. And so all this matrix math we showed, it's really useful in manipulating and organizing data, and that's and like feeding data through values, and that's kind of the core of machine learning. So all of this matrix stuff we've been showing is the core technical background of all of like machine learning and data science. It's just you're manipulating these. So if we want to get the output, okay, of x squared, like 5x squared, right, plus 3x plus, like, I don't know, 10, right? If we want to get that, we can get this using matrix multiplication, all right? Or we can get this from a dot product. The question is, what are we dotting? Can anyone tell me? Anyone have any ideas? If this is what we want to get. Well, okay, wait. First off, guys, be clear. What is the dimension of the output on the right? It's a 1 by 1, right? It's a single output, right? It's a single output. What is the first matrix on the left? 1 by 3. Okay. What's this one? Then what's this one? 3 by 1, right? Does that make sense? 1 by 3, dotted by 3 by 1, 1 by 1. If we want it in this order, I mean, the order doesn't really matter. There's like, let's just say you want it in the order x squared x 1. So it contains 1x and x squared, right? Okay, but okay, the order doesn't matter, so let's just say it's x squared, right?
Plus x plus 1.
And 1. So then what's this second one? If it's x squared x and 1, and you want to get 5x squared plus 3x plus 10, x squared times 5 plus x times 3 plus 1 times 10. So then you get 5x squared plus 3x plus 10, right? This is why matrices are actually useful, because you can represent a lot of things in like algebra, which is why it's called linear algebra, in this matrix in vectorized form, which is why it's very cool. So you can think of it as like data tables can be represented as matrices because they have rows, right? Which is often the sample numbers, and columns, which is often the variables, right? So if you look on this example, even though it's not numbers, just think of it like how, so each row is a different person, right? So like you see, these are names, but each column is a different variable, right? So it's their name, their hometown, their date of birth, when I guess the account was created, when it was updated, right? So those are the variables. So usually the way data is stored is the rows are different samples and the columns are the variables. Does that make sense? So this is kind of like how in a matrix you'd have rows and columns, right? So this goes back to what people are saying is like, oh, can a matrix have meaning? Yeah, a matrix can have meaning as that you can represent data in a matrix such in a way that the rows of the matrix are different like people or different samples, and then the columns of the matrix are the different variables that we assign. Does that make sense? So this is like a way you can represent information inside of a matrix. Yeah, okay, so a data matrix. So essentially we want to find patterns between descriptive variables in the data and like some output goal. And then we use, in often cases, the rows or the individual training samples and their variables to find relationships and correlations. So that's kind of how all this ties into machine learning.
So this gets to the coding part, data structures in Python. So the way that I described a matrix earlier, the way it's kind of represented in like any coding language is usually as an array. So it's like basically it's a matrix in coding. It's a matrix in code or a matrix in coding language, right? So once again, we see 1D array is essentially a 1 by 3 matrix. It's like any like 1 by n matrix. That's like a 1D array, or any n by 1 matrix, a 1D array. 2D arrays are any n by m matrix, right? So this is a 2 by 3. And then it can get even more complicated in coding language, and you can have like 3D arrays, 4D arrays, 5D arrays. It gets very complicated really quickly. So essentially we use like coding platform, like Python to index elements and do matrix operations. Okay, so what I'm gonna be showing you guys is something called the Numpy package or Numpy package. So it's essentially it's like really good for data manipulation and using data structures in Python. You can create multiple dimensional arrays, various matrix transformations, etc. Okay, I'm gonna show you guys on code now. All right, these are basically a bunch of very basic commands, and I also annotated it so you can see I kind of comment what I'm doing each time. Okay. So here, so I'll read what I wrote. We can initialize a matrix that is 2 by 3 with like 1, 2, 3, and 4, 5, 6 using the following command. So what you do is, one thing though is don't worry too much about this, but essentially since Numpy, right, is a package, what you have to do is you have to do import numpy, and then we're gonna call it as np. Oh, sorry, that's wrong. Import numpy as np. There we go. Okay, so then we're saying right here. Okay, so do you guys see this line I'm highlighting?
Yeah.
So what we're saying is np numpy package. So we're gonna use that package, commands from the package. We're gonna create an array, right? I explained array matrix, kind of similar. And then what we're gonna do is so the parentheses indicates this is what we're like, this is like the function call. I don't know how familiar you guys are with code, but essentially you need to have like a function call, and that's inside like parentheses almost always. And then the brackets indicate the matrix. two-dimensional matrix, and then then the parentheses inside that represent each row. So what this right here is, these parentheses 1, 2, 3 is that's the first row, 1, 2, 3. Then the comma indicates now we're on to the next row, 4, 5, 6, right? Then if we run this line in the in console, we get, right, a 2 by 3, 1, 2, 3, 4, 5, 6, right? You see that? We created 2 by 3 array matrix, whatever you want to call it. But yeah, so I created a var1, which is a numpy array that it has, like I said, so bracket is indicates this is the first, like, this is two-dimensional. If you have multiple bracketed things, it goes into 3 dimensions. So we only have one bracketed thing, so that's one two-dimensional. And then inside each one of those, you don't even need the multiple brackets. You could just have one bracket if you needed. But basically, you're just saying, yeah. So this is 1, 2, 3, 4, 5, 6, and then this is the row, column. If I then added another, if I then added like parentheses 7, 8, 9. Then this would be a 3 by 3, and then 7, 8, 9 would be the third row. But we'll just keep it to 2 by 3 since the rest of the stuff is written for this. And then what you can also do is you can initialize using either all zeros. So that's mp.zeros. So right, if we create mp.zeros 2 by 3, it creates a 2 by 3 array that's just all zeros. Then we can also do randomize between 0 and 1. So just do mp.random.random 2 by 3, right? And then once again, we get an array of random numbers between 0 and 1. That's 2 by 3. Okay, so then what can we do next? So how do we do like matrix addition and subtraction? So, okay, so let's do var1 plus var2. So we can do that because they're both 2 by 3. So var1 is 1, 2, 3, 4, 5, 6. var2 is 0, 0, 0, 0, 0, 0.
The same numbers because they're both
right?
0?
Yeah, exactly. 1, 2, 3, 4, 5, 6. We get the same number. But what happens if I do var1 minus var3? var3 isn't all zeros, so now we're not going to get all zeros. We're instead going to get whatever this var1 is minus whatever var3 is, right? So you get this. So you can also do element-wise multiplication. Remember how we explained the dot product and like matrix multiplication versus element-wise multiplication? So if we just do the star in Python, that's element-wise multiplication, okay? So var1, var3, you still get a 2 by 3, and it's 1 multiplied by 0.33, 2, 0.99, etc. And you see that's what you get. There's also the command np.multiply that does the same thing. Except this time we're multiplying it by var2 instead of var3. So you see you get all zeros because it's 1 times 0, 2 times 0, 3 times 0, etc. So it's all zeros. Okay, so the same thing for division. Element-wise, once again, just slash sign, right? 1 divided by 0.33, that's essentially multiplying by 3, which is why it's 2.94, and you see the rest of them are the same thing. And once again, np divide, same command, same thing, right? Get the same thing, same exact command, just different syntax. So we can also do commands like square, which would take element-wise square, so it's all the elements squared, right? 1, 2, 3, 4, 5, 6 squared, 1, 4, 9, 16, 25, 36. Then the command power is if you want to do other powers besides squared, besides raising to the power of 2. So say if you want the third power, right? 1 to the third power, 1, 2 to the third power of 8, 6 to the third power, 216. That's what you see. You want to take the square root, just np.squirt, right? Boom. Square root of it, right? This is why it's very cool, because this by hand, if you do it with big matrices, can be hard. But doing it with just these like automated commands that are pre-written is very easy and fast. All right. Okay. So now if we want to do a dot product, right? So if you look at the dimensions of the matrices I have right on the right in the variable explorers, we can't dot any of these, right? Because they're not the right dimensions. Because none of the columns and rows match up, right? 2 by 3, you can't dot that with a 2 by 3 because the columns and rows don't match up. So we're gonna create a new array that's 3 by 2. So if we create var4 and we look at what var4 is, right? It's a 3 by 2. It's 1, 2, first row, 3, 4, second row, etc. And then now we can do a command np.dot, and we put var1 first because it's 2 by 3, and var4 second because it's 3 by 2. The order of the variables matters here. So so then we put it, boom, right? We get this. You guys don't need to worry about it, but it's like 1, 2, 3 times 1, 3, I think 5. 1, 1, 2, 3 dotted with 1, 3, 5, 1, 2, 3 dotted with 2, 4, 6. And it's just like that. So that it's these two dotted together. Don't worry too much about that. We already went over that earlier. And then the other important thing is we can also index, okay? So if we want to access this, remember how we talked about the matrix containing elements? If we want to index into specific elements, right? You essentially do the name of the matrix of the array, right? So in this case, var1, bracket, bracket, and in the parentheses inside, it's kind of how we represent the matrix indexes, okay? So if we want the first element in code, usually indexes start at 0. So we go var1 bracket 0, 0, 0th comma, 0th row, 0th comma, column. So then that gives the first element, right? First element, 1, right? The first element right here is 1. If we want the first row, you can do 0, comma, colon. What the colon indicates in Python is that you look at all the elements in that specific row or column, right? So the first row, see, if you look at first row, 1, 2, 3, that's what we wanted. First column, now you just swap the location of the 0 and the colon, because now you colon the rows, so it's all the rows, and then you do the 0th column, so it's all the rows, but only the first column. Yeah, so look, you get 1, 4. That's right, 1, 2, 3, 4, 5, 6. First column is 1, 4. The same thing can be done with last row. The reason I put a -1 instead of a 2, because it goes 0, 1, 2, is because if you're working with a large matrix or data frame and you want the last row, you don't want to have to like count or like figure out how many there are. You want to just easily work backwards. You can just do -1. And if you look, last row, 4, 5, 6, that's right. Last column, switch the place of the -1 and the colon. Boom. Once again, last column, 3, 6, that's right. So these are just like some of the basic commands. So this is kind of how you just index and manipulate data frames.